Hello guys, we're going to talk a little bit of RAM here to finish up a problem that takes rectangles to infinity, and this problem's a little bit more involved, so I thought I would do this one online and let you follow along. So here is my function. It is 6x cubed, 3x and a 3, so this one can be done by using shortcut method 2 with the summation symbols. Again, if it's not a linear, if it's not a parabola, if it's not a cubic, and it's not a constant, we do not know how to do it. Here's my zone from -1 to 2. So I'm going to do left RAM first. Here's my delta x, b minus a over n. So there's my common width. Again, an open statement. This is what I'm going to plug into my function, starting point, plus width j. And again, I'm going from 0 to n minus 1. I plug this into my function, the cubic, the linear, and there's the constant. I need to cube this out, which is a little bit of a mess. I did it here. I distribute the 6. I distribute the -3 and the +3. I then combine terms among these values. Here they are. Linear, square, cubic. I will now distribute this formula to each of these. Now this is a constant, so it pulls out. Constant, pulls out. Constant, pulls out. So now I have the sum of consecutive integers. But because it's left, instead of going 1 to n, I have to go to n minus 1. So wherever there's an n, I have to put in n minus 1. That's why instead of n times n plus 1, it's n minus 1 times n, still over 2. Same thing with the squares. Typical formula is n times n plus 1 times 2n plus 1. Well, every n is getting replaced by n minus 1, so that changes this formula. Over 6. And then the cube is the linear formula, but squared. So we take advantage of that. I went ahead and multiplied and distributed. Multiplied this all out and distributed. Multiplied this out and distributed. I then take my width and distribute it through all of these terms. Now I individualized them so I could reduce it. This 45n squared over 2n times this makes this term. Now I reduced it, so there is my constant. Here's a variable for n, constant, variable for n, variable for n, constant, variable for n, and variable for n. Now what this is doing, everything that has a constant, this one, this one, this one, and this one, and that one, that's what's taking away or adding on, depending on the shape of the curve, away from the true answer. That's the error this left rectangle is adding on. So if we go back to the next page here, there it is, I am going to take this formula, which we have in this particular corner. Let me lower it a bit. There we go. Take this formula right here, and I'm using it right here for 10 rectangles. So wherever there's an n, I put in 10. So blow that up a bit. So this is what I would have for 10 rectangles. That is my approximate area. If I do 50 rectangles, every time there's an n, notice how that changes, I put in 50. This would be my approximate area for 50 rectangles. If I had 100, I replace all the n's with 100, and there's my answer. Now, if I want to do infinite rectangles, anything that had an n, here, and here, and here, here, and here, the bottom gets bigger, so the whole thing goes to 0. And I'm left with this case, 3 constants, which adds up to perfectly 27. And that is my area underneath this curve from -1 to +2. That is the cumulative area. So by doing it as an open equation, I am able to find and show how, as n gets bigger, your area heads towards the correct answer. We want to be able to do this. It is nice to do these. Now, as I mentioned in class, it doesn't matter if I would have had done left right, or middle. So I'm going to do the same exact problem, but now I'm going to do it from right RAM. And if I do that, nothing truly changes until the error on the bottom. Here's my formula. There's my range. There's my 3 over n. Same thing being plugged in. Same thing being cubed, linear, and 3. Same thing as the earlier. Distribute the summation, but now, of course, instead of 0 to n minus 1, it goes from 1 to n. So I'm going to have different error when I'm all done. Here is what I end up getting. Now what you're going to notice is 3 things are the same. The 135 over 2, the negative 162, and the 486 over 4. Those 3 appeared in left. They have to be. That's my answer. The rest of the stuff with the ends is your error for right RAM, slightly different than left. So I give you an example here with 10 rectangles. I plug in 10. There's my answer. I plug in 50. You can see my answer has gone down. I plug in 100. It's gone down more. And once again, when I let it go to infinity, this and this and this is the only thing that's left over. Oops, I apologize. This and the 162 and the 46/4. That's the only thing that's left over to give me the same example of answer, I should say, of 27. It doesn't matter if I do left, right, or even if I did middle, which is the third page here. However, if you do notice, on the third page, I did not work it all out. Cubics with middle RAM is a huge undertaking. So I went ahead and at least told you I would set this up. Here's what I need to cube, here's what I need to linearize, and here's the 3. To multiply this out, to distribute the 6 and the 3 and the summation is a waste of time. If you're going to infinite rectangles, the answer to this is still going to be 27. So it makes no difference if I choose to do it from the right way to get 27, or if I choose the left way to get 27. The area underneath this curve from -1 to 2 for infinite amount of rectangles will be 27 any way you think about it. I hope this example helps. Keep working. Thank you.